So let's start with this slide, I think. And previously, we finished with these digital circuits. And now, actually, from the book, it is section 1.3. So this is the third section of the chapter 1 of your book. So here the topic is propositional equivalences, which means you have to find the equivalence between the different propositional statements are different logical expressions. If two logical expressions will be given to you, you have to find that they are equivalent or not, logically equivalent. So normally in mathematics, you are already in practice that if you have some question, you can start that question and then either in that question you can normally let's see it here. So if you have some question here like, and if that question has some parts, I'm not writing text, I'm just giving you an idea. So in the next step, if you want to modify this step, you can code that I am using that rule, and by using that rule I can modify this part to some other part, like that, some other part, and the rest of the parts are same as it is. So this replacement of statement that you normally do in mathematics, this is based on already proved result, and those, for example, this portion which you want to replace it by using this existing rule, because these things are already proved and their truth values are same. Actually, these things are already proved and their truth values are same actually. So that's why this is very much normal practice in mathematics, that you can replace some part or the whole with some other statement in mathematics. So now we will learn some terms and then we will move on to this topic of equivalences. So there is something which is called tautology. That is something which is called tautology. So what is tautology? You will have some compound proposition, and you know what is compound proposition. You know that or not? Okay, good. So when you have two or more propositions joined with each other through connectors, that is called compound proposition. So when you have compound proposition, and if you will find its truth values by using the truth table, if you will find its truth value, and if all the truth values are true, then you call that compound proposition a tautology. Similarly, contradiction, when you have a compound proposition and in its truth table, if all the values are false, then that compound proposition would be called contradiction. And if it is a mix of true and false values, then you can call it contingency. So let's have a look. So here we have a truth table of this compound proposition and this compound proposition. So this is compound proposition connected with this or and connected with this and. So if you will calculate or if you will evaluate their truth tables, then you have, for example, here you have two variables, p, only one variable, sorry, p, and how you can find the negation, it is written here. And then you are going to find that it's the first part, and then the second compound proposition, and you have the values. So here, when you have all the values true, then you can call this compound proposition what? A tautology. And if you have all the values false of a compound proposition, then you can call that compound proposition what? Contradiction. Here we don't have any example of contingency, but if it is a mix of true and false values, not fully true, not fully false, if it is a mix, that is called contingency. So now, Before starting this equivalence, logical equivalence between two compound proposition, we are basically learning some terms which we will use. So up to now, we know that compound propositions, if they have the same truth values, then those compound proposition would be what? Logical equivalent. This is the only method we know up to this point if we want to find that how the two compound proposition are equivalent or not. This is the only method we know that we will find its truth table. And if their truth values are same, then we can say they are logical equivalent. And we don't know any other methods. So now we are moving towards another method which we use for finding the logical equivalency equivalent. And similarly, when you will move on to maybe CO3, then you will find another third method for finding the equivalence. But the first one through truth table is easy. And the next one, which is coming now at the end of the CO, that is something through replacement of statements. That is something through replacement of statement by using existing rules. So anyhow, if we have two compound propositions P and Q, if this P and Q, suppose these are variables, but consider it as a two compound proposition. Just assume that these are big compound propositions. And if you want to show them that these are logically equivalent, then this is the symbol we know that. So P logically equivalent to Q. This is one thing we already know that. This is the notation. But if you will find the P by implication Q between these two compound positions, if you will find this P by implication Q between these two compound proposition, and if the values in the column of this P by implication Q are true, means if they are tautology, then you can call that P and Q are what? Logically equivalent. This is now the second method. Now you know. This is again through truth table. This is again through truth table. So you one method that you can find the truth values for P and for Q, and then if the values of P and Q are same, you can call it they are logically equivalent. Now the second method is you have to find what? You have to find P by implication Q between these two propositions. And if the values of the columns are what? All true, means if the values are tautology, if this by implication is tautology, you can call that this P and Q are what? Logically equivalent. This is the second method now you know. So this symbol by implication, which is written here by using the PowerPoint, so that's why it looks different. Otherwise, I want to say the same thing. Okay. So that is same. So in PowerPoint, this symbol is available like that. So that's why it is like that. So no issue. It means double arrow. It's mean by implication. So this symbol, we can also use this symbol in place of these three lines, which means the logical. In some literature or in some books, you will find this symbol in place of that, and that means what? You know that through this definition. Now, the example is show that one of the De Morgan's laws in table 2, this is table 2, and two laws are given here, show that one of them is equivalent. So the question is, you don't have to show both are equivalent. Here you have the left hand side and here you have the right hand side. Similarly, in the other left hand side and right hand side. So you don't have to show both of these. Just go with the one, any one. But here, so in this example, we are going with the second one. You can also go with the first one if you want. So you show that they are equivalent. What it means? Show that one of the law in table 2 is equivalent. You have to show that the left hand side of this rule is equivalent to the right hand side of this rule. You can also show that the left hand side of this rule is equal to the right hand side of this rule. You have to show they are equivalent. Left hand side is equal to the right hand side. This is what you have to show. But the question is, you can go on with any one, not both. So we are going here in this example with the second one. So what you have to do here, you have how many variables? Two. So that's why P and Q and their values. And then you have to find what? Disjunction. So here is the disjunction. And then you have to find negation. After finding the negation, here is the values you have, triple FT. And then on the now you can go on to the right hand side, and here you have the negation P that you have to find. So you can find negation P and negation Q from these values, and then after that you have to find the conjunction. Okay, now finding the conjunction between these two between these two columns, and then you will have these values. Now if you are matching these two columns, triple FT, triple FT, so the values for the left hand side column, or you can say the values of the left hand side are equal to the values of the right hand side. So this is what the method you already know, the first method to show equivalence. And if the values are same, then what it means? It means what it means? It means the left hand side is equal to the right hand side. Left hand side is logically equivalent to the right hand side. Why? When I say equal, it means logical, because we are in the field of propositional logic. And what is the definition of by implication? So by implication, Q is true when P and Q have the same values. So now let's have a look over here. If you will, if you have to show P by if you have to show this one and this one, left hand side, and the by implication right hand side, if you have to show, okay, by implication according to this previous definition. And if you apply by implication between these two columns, so they have the same values, they have the same values. And when the values is same, what you will get in by implication? In by implication, what you will get in this by implication? Hmm? Tautology, but true values. This is the simple thing, and you are not following me, huh? I can, so now on the whiteboard, I can ask you something like that, P or Q, these triple lines, and then negation P and negation Q. I can ask you to show that they are logical equivalent, show that they are logically equivalent by showing what? Negation P R Q, double implication, negation P and negation Q. Then what? You have to do this whole table 3 as it is. And then, for example, this is your table 3. And then you have one column extra. That would be this column. That would be this column. What is that saying? So negation P, sorry, P R Q by implication, negation P and negation Q. You have to find what? By implication. And now that would be between this and that. So this is available, negation PRQ, this is available here. What are the values? Triple F. And what is that? That is also available where? This one. So now, if the values are same, what you will get here? True, and true. So then this is what? Tautology. And if by implication, then you can finally say that if their by implication is tautology, hence left hand side is logically equivalent to the right hand side. Now you have to make the decision at this time. If I modify the question. Okay.
If you have to show by implication, it is one step ahead than this first step one. It is one step extra. Okay. So then for by implication, for this by implication, you can find that the values are same, and then you will get tautology, and then finally you can say that the due to tautology of this by implication, we can say the left hand side is logically equivalent to the right hand side. And now this is another page, and on this page there are many rules that you have to memorize if you want to solve the questions which are coming next. Okay, so that would be again a hard task, huh? So, but this is what you know normally a student do in their early studies. So here you have a table 6, and in this table 6 there are different rules mentioned here. These rules are already proved rules. You only have to memorize them, and then these rules you can use in upcoming questions to solve them, that the left hand side is equal to the right hand side or not. Similarly, here you have table 8 with some rules by using this by implication. These are the rules with by implication, and these table 7, these are the rules with simple implication. So here, if you just have a look, just one or two, so P and true, and P and true. So you have some proposition P, you have some proposition P, and then it is conjuncted with T. So whatever you will get, for example, here you will have F here. In place of this P, you have what? F here. And F and T, you will get what? F. And if you have T here in place of this P, and then conjuncted with this T, what will you get? True. So whatever the values of P would be, you will get those values here. You will get those values here with this conjunction. So P conjuncted T, logical equivalent to P, and similarly with or, and then you have F, you will again get B. So it's easy. The name of this law is identity laws. Similarly, P R T. So whatever have, when it is disjunction, you will get true, and when it is conjunction and only one false value can make it false. These are called domination laws. And similarly, P or P, when you have a proposition and you are conjuncted with itself, then you will get P. Similarly, for this conjunction, you will get P. So you have to memorize them. There is no any other way. Okay, you have to memorize them. There is no any other way. One way is that I can give you this whole table in the exam. No, I will not. Okay. Okay. Why you are going to go with the easy approach? Okay, keep something in your mind so that it would be good for you. So if I will give you these tables in the exam, then the question which I will give, that would be hard. Okay, and if I will not give these table to you, then the question will be moderate, average. So anyhow, so this negation into negation P, so negation multiplied, and then you have the P, that is called double negation law. Similarly, PRQ is equal to QRP. That is your commutative law that you are already seeing in the mathematics in your previous courses. So commutative laws. And similarly, P or Q and then or. And I can just put this P out, and then I can make this Q and R in the parentheses, nothing else. So we are just changing the position of the parentheses, nothing else. So this is called associative law. Similarly, here, this one, P and the or, and then you have in the parentheses something conjunction, Q and R. And then what will happen? I am making this pair P and Q, P R Q, and this symbol which is out, keep it at out, P R Q, like that, and then what? P or. So P or, and this symbol which is inside the parenthesis, it is still inside between these two things. Just what I am saying these different sentences to memorize the pattern so that you can memorize that formula in your mind. Similarly, these De Morgan law, we have seen it here now. It is the conjunction. It is the negation of conjunction and it is the negation of disjunction. And what you will get, just multiply these negation P and then symbol is changing and is going to change in or and then negation Q. Similarly here. And so what you have to do, you have to memorize them. Let's see an example where we are using these different rules. So we are here, we will see how we are using. Okay. But first, have a look on this. De Morgan law is what it is. It is the negation of conjunction and it is the negation of disjunction. Okay. And here we have an example. Use De Morgan laws to express the negation of this sentence. A sentence is given. This is one sentence. This is another sentence given here. Two sentences are given here. And the question is use De Morgan laws to express the negation of these two sentences. It's easy. It's not difficult. For example, if you have a look over here, if Miguel has a cell phone, if you will call it P, and is what? Conjunction. And he has a laptop computer, if you call it Q, then you have what? P and Q given. And what you have to show, use the De Morgan laws to express the negation. Now you have to apply uh, apply this rule that you have here. Now you have to apply this one. So P and Q is given to you, and then you have to apply this negation symbol. What you can do, it is not the case that Miguel has cell phone and he has a laptop computer, then it would be equal to this left hand side. If you will introduce, it is not the case. It is not the case that, and if you will write that sentence, then that would be equal to this left hand side. But for the right hand side, okay, now you have to express this. So negation P. Miguel has not a cell phone. And this becomes or. Miguel has not a cell phone. Or, and then you will write or. And he has not a laptop computer, nothing else. So you can say this right hand side is equal to like that. So this is available in the book, page 29. So you can read it by yourself. Hmm? Hmm? Book? You are asking for the book? It is available on the internet. Why you have not tried by yourself to search that book? But I will share. Just give me a message on the WhatsApp group and then at night, so that I will be at home. Okay. So give me a message on WhatsApp group and then I will share the book on WhatsApp group. So now this question, the important one. So we now can use table 6, 7, and 8. These are the table 6, 7, and 8 of rules. So now we are going to use them. We can use these 6, 7, and 8 to prove to show some logical equivalences between the compound propositions. And now we have an example, and this example is saying show that this thing and this thing are logically equivalent. If the question is ended here, anyhow, if the question is ended here, then you are free. You can use truth table, you can use by implication, or you can use this method. Okay. But if something is written here with that logical equivalent question, show that this thing and this thing are logically equivalent by developing a series of logical equivalences. So you have to develop the series of logical equivalence, which means there are some rules which are available as a logical equivalencies. So you have to use that rules to prove that this one thing is logically equivalent to the other thing. This is like left hand side and the right hand side, like that, but written in this way. So then what? then how you can solve the questions like that? You can take any one side. You can take any one side, but in the questions like that, it is always good to take the lengthy side, because reducing the lengthy side to short one is easy, rather than you will take the short one and expand it to some other thing. So that would be difficult for you. So anyhow, uh, so we will take any one side, and then we will keep on modifying its different parts by using some existing rules. These existing rules, which are in table 6, is 7 and 8. And then we will try to modify this thing into the other thing which is given in the question. And if we will be successful, this is what you have shown, that this thing is logically equivalent to the other thing. So that's why we are taking this side, which is a little bit lengthy, and it is what? Negation P R, negation P and Q. So we are just writing that thing, negation outside, and then parenthesis over it. So the first thing we can do here is, for example, if you will look here on this side, then you have negation P and negation Q. So you need negation P and negation Q. So here negation is outside. So one thing which is, you can just simply uh, understand that we have to multiply this negation. We have to multiply this negation. We have to multiply this negation. And this is one thing, one part, and this is another part. So if you have this De Morgan law, if I remove these things, if De Morgan law is in your mind, then it is between the two things. And then you have the conjunction and negation outside. And similarly, you have two things. These PQ can be compound proposition, can be simple variable, and the disjunction, and you have negation outside, and then you have to multiply it. Negation P, inner symbol change, and negation Q here also. So now, if you will look over here, so this portion is one thing, then disjunction, and then you can consider this whole thing as a one unit. Okay. So then what? And negation outside. So then you can apply the De Morgan law. And what is that one? Disjunction is the second one. Disjunction is the what? Second one. So we are by applying, or you can say by applying the second De Morgan law, or you can say by the second De Morgan law. By using second De Morgan law on this part, we will get what? Okay, negation P, and here negation will multiply with this whole part, and you will have here negation into negation P and Q, and this inner symbol will be changed. Conjunction will be changed into what? Disjunction. So this is what you have applied the second De Morgan law. Now, so this negation P, we want this negation P, but we don't know. There are no fixed steps that you can identify. These are the questions which you can solve only through hit and try. If some supposition you are taking, and if it is okay going in the right direction, that's okay. If not, then you have to come back and you have to change some other rule or whatever. So there is no any fixed thing here that you can find, okay, here I can apply that rule or that rule. Sometimes you apply some rule which will give you the wrong direction. It can happen. So anyhow, so now this negation, but from the things that you have to go logically. So here negation P, I have that negation P, but I don't have this and negation Q, which is here on that second part. But anyhow, so in the second part, now I can go on with this negation into negation. I can simplify it because it is becoming complicated for me. So I want to open it up so that I will have all the things clear. So that's why here again, if you will look here, the negation outside, then you have one thing, and then you have another thing, and conjunction inside. So this is what? This is that rule, first law of De Morgan. So now by applying the first De Morgan law only on this portion, only on this portion, I'm not talking about that part, only on this portion. So and then what you will have? Negation into negation P, this is that. This will be changed into disjunction, and this Q, due to this negation, it is negation Q. So this is what, by using the first De Morgan law. Clear? 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 Okay. So now here in the next, okay, this negation P, this is negation P, Q I want. Is it possible for me to remove that portion, and then maybe I will close to my answer? But anyhow, I cannot remove it without using some rules. So then what? This is negation into negation. So by using the double negation law, this is what negation into negation will become positive. Anyhow, so this is negation. This is again the same. I am not doing anything here. Only this part. I am handling only this part. This upper portion. Negation into negation will become what? P. And then disjunction, and then this negation Q as it is. As it is. Now, if you will have a look over here, so we have this thing. So this is negation Q, then and there is something in the parenthesis, and then you have something like that. So do you have some other rule here available here? If you will look here, this is, so then something outside, this is disjunction, then within the parenthesis. So this is the form now you have there. So that is what? That is distributive law. So I don't know this disjunction and conjunction inside, and conjunction and disjunction inside. So let's have a look here. So now this is the form negation P, and then conjunction and disjunction inside. So by using that law, which is called distributive, whatever the law here is, you can simply say by using the distributive law, not first second. Okay, you can give me just by using distributive law. Then what will happen? I know that I can make the pair of first one, this with this one. So then we, and I can make the pair of this first one with the second one. So these two pairs I have, and I will keep this disjunction between it. I have the pattern in my mind of. So then what? Negation P and that P, I am making that pair. And then negation P and negation Q, I am making that pair within the parentheses. And I am using this conjunction, which is outside. So I'm keeping outside. And this inner symbol is still between those two things. This is the pattern which I have in my mind from that table. So by using that distributive law, now I have this form. Now I have this form. So now this negation P and this P, this is becoming equal to what? F. How it is becoming equal to F? So let's have a look. This negation P are P or negation P. Okay, P or negation P, and then it is become equal to true, and then P and negation P, it is logically equivalent to what? F. So by using that negation law, this one, with conjunction, by using that law negation, so now this is what? I have the F here, and then this remaining are what? What is the remaining? This disjunction and that portion as it is. So you can write here by using the negation law. So here it is written like that this is equal to F, but you can write other statement that by using the negation law. Double negation law is different, and only negation is different. So now this is one part, and this whole thing is another part, and disjunction is here. So now I am using commutative just to change the order. That is not needed. You can go directly from there to that answer. But anyhow, you can see here. So, for example, in mathematics, in sets A, B is equal to BA. That is commutative. Okay, so that is here. F, something like that. So by using the commutative law for disjunction here, if you will, here, this is the commutative. PRQ is equal to QP, PRQ first or P. And similarly, P and Q equivalent to Q and P. Just changing the position. So here you will change, and this first part will come here in the beginning, and then this same operator here, and then this F will come here on the right hand side. This is what how you have done it by using the commutative law. And finally, something you can consider this as a whole unit and then this f as a whole unit and disjunction between them. This is one law in those tables that is called identity law. Have a look here. So this is one p r, this is one p or f. This p is some proposition, compound proposition, and then or and then f, logical equivalent to what it will, you will get p. So that's why here, so you can consider this whole portion the p or f, and by using that law you will get this whole portion, which is what negation p and negation q. And this is what, this is the other thing, this is the other part which is given in the question. We started with this one, we started with this one, and after modifying, after using the replacement of statement approach, now you have read on the other part which is given in the question. And if you are successful in doing that, then this is what you have shown, that those two parts are logically equivalent to each other. Okay, so now therefore it is written here consequently. So in a sequence, finally we have a conclusion that this compound proposition and this compound proposition are logically equivalent, are logically equivalent. So this is the end and this is the assignment. I have uploaded this assignment on the Blackboard. You can see them there. That is easy. And I have not introduced the deadline yet. So, but you can consider it by default 1 week. So you have to submit in the next class of the next week. And now we can start with the